but I would like to convince you that today we are able to use large-scale models of cortical networks as digital twins and research platforms to address questions that we have not been able to address before. And I will also talk a bit why this may be important for future AI. Need to find out how this works. Can also use the buttons.
I don't want it should work. Yeah, I will do this.
Okay. Okay, so as neuroscientists, we want to understand brain function. This is still our main drive, but with the events of recent years, I think we have so another responsibility that connects us directly to society, and this is that the modern AI algorithms are optimized for present-day computers, so they run well on the computers we now have, but we are still paying a terrible price for this. That is expressed in these two numbers here. Our brain consumes about 20 watts, and the supercomputers we have consume about 2 megawatts. The recent system that at our place that became online a few months ago consumes not less power, but even more. It now consumes 20 megawatts. So that means there are 6 orders of magnitude in between. So, and if there is a discrepancy of 6 orders of magnitude, you can imagine that there's something fundamentally wrong. So somehow AI is fundamentally on the wrong path. And can we do something with this easily, this technology? No, because we are reaching the end of Moore's law. That means further miniaturization becomes harder and harder. So we need to think harder and try to build new computers using principles of the brain. And so another way of showing how dramatic the situation is this graph here. Here you see the temporal axis going into the 2040s and 50s. And here you see in the yellow line the world's energy production. And the green line here is the prediction on what fraction of energy is used by computer technology and largely AI. And you see if this prediction would be true, we would use all our energy that we can produce at around 2040 for AI. And of course, this is not going to happen because we use electricity for other interesting things like heating water, light, air conditions, and so on. So meaning that the progress here will flatten out. And also, this has other consequences. Yeah? It means that the computing is only available for people who can afford it, for the big tech companies, and so on. So it will have an effect on democracy. We need to do something against. And then this raises the question, is there any hope that we can do something about it? And this hope is expressed here on the right side. Here you see a photograph of a neuron. This is the length scale. So the diameter of the cell body here is about 20 microns. And here in the lower part, you see a photograph of a modern transistor. Here the length scale is about 20 nanometers, meaning that we already in our technology, we can produce structures that are 3 orders of magnitude smaller than the relevant structures in the brain. And also, if you look at the number of elements, then the number of neurons in the brain looks immense. In the human cortex, we have about 10 to the power of 10 neurons. But also this number is something what we can do in technology. In a modern microprocessor, there are about 10 to the power of 10 transistors. So I don't want to claim that a transistor can do everything that a neuron can do, but roughly it shows you that in technology we are on this level. And because we are 3 orders of magnitude smaller, it also means that the switching times are smaller because they largely depend on the capacity of these electrical devices. So there seems to be room to maneuver. The actual problem is the wiring. So on the right side here, you see another photograph, but this time with a different staining. The length scale is the same, 20 micrometers, but now the outgoing structures of the neurons, the axons, are colored in black. The white spots are not neurons, but blood vessels. And you see that all this space is completely filled by wires. The brain is densely packed by wires. There are about 3 kilometers of axons per cubic millimeter. And this 3D wiring we cannot achieve in technology. Our technology is largely still 2D. But because we have this factor of 3 orders of magnitude smaller, we can also play other tricks like multiplexing and so on to overcome this problem. So it does not seem to be hopeless. And also from the theoretical perspective, there is some hope that rests in the universality of the neocortex. Yeah, for theoreticians and engineers, if we want to produce something, we need to rely on that there is a principle that we can follow. And what you see here are cross sections of brains of different mammals. Here is the mouse, here is the human. And what you can see is that all these brains are very similar, especially in this outer rim, what we call cortex. If you zoom into the structure, you see that locally on a cubic millimeter scale, all these brains look very similar. So it seems that somehow in evolution, nature hit on a principle that was so important, so precious, that it just makes sense to build more and more. So the human brain has an increase in volume compared to the mouse of about a factor of 1,000. So this is one universality, and the second is that independent of what the cortex is processing, whether it is auditory information, visual information, or motor planning, also there, the brain structure looks roughly the same. So it made sense to look closer into what this cortical microcircuit, the network within the cubic millimeter, looks like. So starting with the work of Douglas and Martin in 2004, they called this the canonical microcircuit. Researchers started to build models of this circuit. We also contributed one in 2014, but we were not the first and of course not the last to get a further insight into the structure. And I will tell you a bit on where we are today and also the difficulties that were overcome by the community over time towards this goal. So this is our model that appeared in 2014. We had the plan to provide this model to the community as executable code on platforms like this, so that other researchers could build on it and do more interesting things of it. But also already in this original simple model, we could get some insight. The model integrates about 50 experimental papers. Here we were particularly interested into what the role of the structure of the network is. So in order to see this, we made all the neurons identical in their dynamics. Also excitatory and inhibitory neurons are identical. It's only that excitatory neurons make only excitatory connections and inhibitory ones only inhibitory connections. And we made the model large enough so that it represents all the about 100,000 local synapse neurons and all their synapses. And on the right side here, you see a typical simulation result. If you simulate such a network, this is time. Here is the surface of the brain, and we are looking down into the depths. The spikes of excitatory neurons are marked in blue and of inhibitory neurons in red. And you see that there are different spike rates in the different layers. This is in accordance with physiology. And that the inhibitory neurons have a consistently higher spike rate than the excitatory ones. This was already known at the time, but it was always contributed to the inhibitory neurons being special, so that they have are more excitable, have shorter time constants, and so on. But this cannot be the explanation here, because here we make all the neurons identical. So here, this is an emergent effect that emerges by the structure of the network. So, and then after the publication of this model, it had some effects. So there are several studies appeared that use this model for different purposes. It was also well cited, but what was more important for us is that there are also, these are the blue ones, a number of citations that not only cite the scientific work, but really reuse the model for other purposes, because that was our goal. And then after 10 years, we assembled a workshop at the University of Aachen, together with a philosophical institute, where we wanted to find out what was the impact of this model on neuroscience, and what were the reasons for the limitations of acceptance and its success. And this publication here is then a report on this workshop. And what we found out is that the model had impacts in 5 fields. The first one is quite obvious. So the model itself produced some neuroscientific insight. It was, in a limited sense, used as a building block for further studies. It has been used a number of times for the validation of mean field theories. That's, of course, also important. It was used for trying out new computer science methods of model sharing. And a bit surprisingly, it became a de facto standard for as a neuromorphic benchmark. I will tell you a few more things about this point. And what probably helped the model initially was that at the time there was not only the model, but there was also a simulation code, also already quite mature, that is the simulation code nest, that people could also download, and by this directly execute the model, arrive at new results without doing any programming on their own. The simulation code is maintained and governed by a public society, the NEST initiative, and there are regularly tutorials and trainings on this software. The next one is, I think it's just starting at the end of the week in Halifax in Canada at the CNS conference. So here is an indication that this simulation code has reached a high level of maturity. This year it was included into the SPEC CPU 2026 benchmark. This is a benchmark suite that is assembled by a consortium of researchers and industry, where they build a set of codes to test new generations of CPUs and so have a fair comparison of different brands and different types. The last set was released in 2017, so this is not happening too frequently. And this time, the number of codes was increased to 52 with an additional 9 since 2017, and Nest became one of these 9. So what are reasons of the limitations of the impact of this model? You have to think back to 2014. This is 10 years ago. Initially, simulating the model required a compute cluster and several minutes for just 1 second of biological time. And also, this network has no function. It just reproduced the physiology. And this is probably too boring for many people. They want to see some function, that the network is doing something, like recognizing the MNIST data set as Sonja showed you. So this was maybe a psychologically major reason for the limited pickup. And it did something outrageous from the theoretical physics perspective. It was not formulated in the minimal model spirit, but as a digital twin. Today, of course, we have digital twins everywhere, but at the same time, there was a lot of criticism on this model that it contained far too many details for the phenomena that it brings out. And another interesting point is this one here. Sometimes we hear our colleagues saying, I don't need these models that use an HPC cluster or a supercomputer. All I'm interested in, I can do on my laptop. So this is, of course, a statement that there's no way that this can be philosophically sound. Yeah, why should the interest of a researcher depend on what industry provides us in laptops that are based on like office work or gaming industry? And imagine that high energy physics had stopped at tabletop experiments. Yeah, we would not have particle physics basically. So the workshop participants concluded the specific model can now be simulated on a laptop and faster than real time on a single compute node. So one of the initial limitations is gone, but also the education by the International Advanced Computational Neuroscience courses may have changed the situation because the new generation of researchers is more used to work with these systems. And this goes so far that sometimes when we give these tutorials I talked about, and we ask the students to install something on their laptops, we observe a feeling of awkwardness among them, because they are so used to work with the cloud that it seems foreign and somehow not clean to install something on their laptop. So in this sense, we are on a good way. But non-neuroscientifically, of course, the model also had shortcomings. For example, if you look at the power spectrum of the activity in this model, then there is basically no power in the low frequencies, whereas in the brain there is substantial power at the low frequencies. And this originates from the fact that in the model we are describing all the synapses between the neurons, but each individual neuron receives 50% of its synapses from outside this local circuit. So you could as well say that the circuit is still heavily under constraint. So in order to improve this, we thought about how can we usefully expand the model. There are different ways of doing this. So this symbolizes here the model we are looking at presently. If you would zoom out a bit, you would discover that the network is spatially organized. The further two neurons are apart, the less likely it is that they have a connection. And if you zoom out further, you start to see cortical areas. In the human, there are about 100 areas, but each individual area is only connected to 10 others. So even on the highest level, there is still room for an interesting recurrent network. So we have to consider this as a network of networks with at least 3 levels of organization. So how do we address this? In the meantime, our field also has made progress conceptually in the sense that we now have a clean separation between the mathematical description of a neural network model and generic simulation engines that can simulate such models. This is not trivial. Not all branches of science have this. If you think about climate research, they are basically the simulation code they have, which is much more complex than what we need, is the model. There is no formal separation. But here in our field, we are in this lucky situation. And this simplifies our problem a lot, because we can have many different models that can be simulated with the same engine. And this means that we can regard this engine as an infrastructure and further optimize and validate this for a long time. And also, there are maybe some models that are simple enough so that we can run them on different simulation engines. So although they may have their main application domain in slightly different areas, or may even be strongly supported by hardware in the field of neuromorphic computing. And this is also a good aspect because it enables us to cross-validate these engines on the highest level. Of course, they should all give us the same results, otherwise something is really wrong. So, and with this progress, we are able now to build models that go beyond the scope of this microcircuit. And the first thing we were interested in here is to connect the local connectivity with the large-scale connectivity of the brain that is supplying this 50% of missing synapses. So at the time, we considered the visual cortex of the macaque as a good model, because there we had excellent anatomical data available. The visual cortex of the macaque has about 32 areas, which make up together about 10 to the power of 9 neurons. It's possible to simulate 10 to the power of 9 neurons on the supercomputers we have today. However, at this time at about 2018, this was still way too costly for production work. So we decided to place in each of the 32 areas one of these microcircuits as a representant and connect them with what we know about the large-scale connectivity. And this then ended up in a model of a few million neurons, which is easy to do on an HPC cluster. And in this model, then we started to see more interesting phenomena. For example, there is a metastable state of activity where in the different areas the activity goes to large fluctuations, as we see in nature. And this then brings us the low power in the power spectra that we were missing. And also the distribution of spike rates now fits much better to the experimental data. And if we look at the correlation of the neuronal activity between areas, so here are the 32 areas, here and here also, and the matrix elements here show you the correlation, then this matrix fits already to some degree to the functional connectivity that experimenters measure in the fMRI in a living monkey. Yeah, that shows you that this network also really brings out the realistic activity on this brain scale. And so this is an average over 6 monkeys, and if you look further into the details, then you see that the discrepancy between our model and the experimental data is not larger than the discrepancy between the monkeys. So in a way, we have even explained everything that is there to explain. And from this point on, we now see more models that work on this scale, but go into other neuroscientific questions. for example, transfer this to the human, which is then more relevant for legal research, address the spatial organization, which was neglected in this first model, or look at the role of different cell types. So, and also on the more microscopic level, there are improvements. This is a work by first author Anno Kurt, who is here among us. And this is considering more solid anatomical data. Now, the data that our original model was based on is largely light microscopy, but electron microscopy was always there. And electron microscopy has the advantage that you can really see the connections between neurons. So you can see individual synapses. However, up until a few years ago, there was no way of really using this on the scale of a cubic millimeter into quantitative data, because the sheer data volume was too big. But with the AI methods we have today, we can really segment out neurons and synapses. This was also a lot driven by the Allen Brain Institute. So we are in a different situation here. Still, there are problems with the resolution, and to show you this, I brought you this picture. So here you see in the gray background, you see the dendrite of a neuron, and on this straight dendrite, you see a thin blue line, and this is the axon of another neuron, and that makes these red dots here, and these are the identified synapses, but the axons are still so thin that they are often not reconstructed. But anyway, on the basis of these electron microscopy, we can now build much better models, and we already achieved one result, and this is the following. When you have a source neuron, then you can compute the relative probability of making a connection to an excitatory neuron versus to an inhibitory neuron. This is what we call the target specificity. So if the target specificity of the source neuron would be 1, it would mean that it exclusively contacts excitatory neurons. If it's -1, it exclusively targets inhibitory neurons. And in our 2014 model, we had to make the assumption that some neurons have a negative target specificity. Otherwise, the circuit would not be stable. And with the electron microscopy data, we could now confirm that this is really true. So a hypothesis that we made 10 years ago is now luckily, it's really fulfilled. At the time, we only had weak indications from physiology that might be the case. And so how accessible is all of this? I already talked about computation in the cloud. On this platform here, built by the European Union, you can download the simulation code, you can download the models, and you can even download something that is called the eBrain software stack that gives you a well-curated package of all these tools together. And if you have computing resources that are attached to this platform, you can even do your computations in the cloud. So this is all based on conventional computers. I already mentioned neuromorphic computing in the beginning. Here you see 2 of the large-scale systems that we have in Europe right now. This is the Heidelberg brain-scale system. Mihai, of course, knows all about it. And this is the Spinnaker system. It's a digital platform built up in Manchester a while ago. And the availability of our model that was then first simulated on a neuromorphic computer in Manchester, sparked something like a constructive race on different platforms for ever faster simulation times and fewer energy consumption, as you can see on these publications. And this then also motivated us to make further steps in the software technology on conventional computers. And with Anno and others, at some point, we also improved the software such so that we could also simulate the model on a single compute node in real time. And that's I brought you this slide because when we talk about the success of neuromorphic computing, which is a big effort in technology and costs, it's of course relevant to have an objective criterion. So is this now progress or not? And so we need to compare it to something, and of course we can compare it to conventional computers as they are mass produced, which is only fair if on the conventional computers you do all that you can to make them as fast as possible. And there are two measures of success. One is the real-time factor, telling you so how much slower is my simulation compared to biological time. So at the beginning, you see here that our simulations were 6 times slower, and now the best systems are like 20 times faster. And another measure is what is the energy we consumed per dynamic event. And what you can appreciate here is that this constructive competition led to a situation that over just a few years, the real-time factor and also the energy consumption dropped down by 2 orders of magnitude. Yeah, and this comes back to my initial statement that if there are 6 orders of magnitude available between brain and what we have today, then the first wins should be easy. And this is certainly also part of what we see here. And just for illustration how wild the systems look like today, this is an immensely expensive computer that IBM built, INC 3000. I think there are only like 2 or 3 in the world. And this is the first system that achieved this 20 times speed up, built by an electrical engineer at the University of Aachen. And after this race was going on for a few years, we decided to write all together. You see this large list of authors here, a review paper where we bring these data together and try to draw some conclusions from it. And while we were doing this, we renovated this website here, so that here you now find really a solid mathematical description of the model, test data for verifying the simulation, the model code, but also a database for collecting publications on the model, so that we can also add further data points. And this website also generates automatically this plot here that brings the different systems into relation. So here you see, for example, how the real-time factor is related to the energy per synaptic event, and you see how all these points nicely fall on a slope of 1, basically meaning that your simulation needs less energy the earlier it terminates. Yeah, and this is something natural for such a system. It uses some baseline power, so the best thing is that it runs as quickly as possible. The different colors here mark the different system types. So GPU is pink, orange is conventional, blue is neuromorphic, green is FPGA based. But the most interesting plot probably is this one. So this is again the real-time factor, but now as a function of process node. And process node is basically the relevant structure size on the semiconductor, so the width of the wires. And as technology progresses, we make the wires thinner and thinner. You probably know this from advertising by Intel and AMD. And here we see that all the data points of the conventional and the GPU systems nicely fall on the slope of 2. And this is exactly how it should be, because if you reduce the structure size by half and you have a 2D technology, then you get 4 times more transistors on it. So if the software developers here do their job correctly and they exploit this parallelism that you have to the best, then they should be on this line. So electrical engineer would not be surprised about this. They would say, well, this is just scaling, technology scaling. This is how it should be. But for us, it has a very disappointing point, and this is that here we are coming to very small, non-existing process nodes, but there's some consensus that we would like to see a speed up of 100 compared to real time in order to study learning and plasticity. However, there are also other data points in this plot, and these are the neuromorphic ones and the FPGA ones. They also, with a very roughly, may fall on a slope of 2, but this line is shifted to the right or downwards as you want by a factor of 100. And this is what the electrical engineers call architectural innovation. So by changing the architecture, the computing architecture, you can really make these big wins. And then we have a chance with existing technology to achieve these speed ups. So, and as technology progresses, we now get first results for neuromorphic simulations on these for these larger models. And at present, at our site, we are building up a new Spinnaker-based supercomputer. You see this here in the early stage of being built up. These are 2 racks, and we are very hopeful that we can run this multi-area model on this computer. This has not been possible in Manchester, although we tried for more than a decade. And then this system has the chance to, for the first time, be faster than conventional supercomputer because of the reasons that I explained to you. So I mentioned that we would like to have the speed up of 100 for learning and plasticity, but all the models that I showed you were just static networks. Because there is this immense difficulty of harnessing this progress that the community made in training artificial neural networks to the spiking domain. Mihai has contributed to this a lot. Sonia showed some results. And in this study here, we tried to make one of these ideas ready for large-scale simulations. This is called prop. It was came out of the book of Wolfgang Maas in about 2020, and this removed one obstacle, and this is in the original backpropagation algorithm. As the flow effectivity moves forward in time, you have to save the state of all points in time, so that in a backward pass, you can revisit the states and update your synapses. And the book of Wolfgang Maas removed this problem by a clever trick of using learning signals that you would have available in the brain, like dopamine or other things. But they still formulated their framework in the time-driven scheme as it is used in artificial neural networks. And so our goal was to translate this time-driven algorithm to the event-driven algorithm that Nest uses for efficient computation, and by this really exploit the spatial temporal sparsity of neuronal networks. And at this point, the results should really be identical. Just the computation should be more efficient. And then in the next step, impose further biological constraints that we have, like delays, that there is sequential learning and so on. And this we achieved in this work. So the synapses are only updated when needed. This means pro and pre-synaptic spike, and the postsynaptic neuron stores the history of the postsynaptic spikes. This was something that we were already using for STP, and there may be an intermittent advance of the synapse to avoid overall histories. And these are just, without going into details, few slides convincing you that we can really reproduce what the original EPROC was doing. So you can have do regression where you have a drawn infinity symbol that the network can track, or you can have more complex tasks of evidence accumulation where an agent collects information and then decide whether to move left or right. This is also what the model can do. And the learning performance is really the same as the original formulation. But then once we had this, we can do a number of steps that I have shown here that bring this model closer to biology without the loss of performance. So this means, as it is often the case, that you need to constrain a model quite severely in order to be able to do mathematical proofs, be sure of convergence and so on. But this does not have to be all fulfilled in biology to work. Very often you can relax these conditions and still have a working system. And the result of this is that we now have a system that fulfills our requirements of scale. One usually distinguishes strong scaling and weak scaling. Strong scaling means you keep your problem size fixed and you increase the number of computational resources, so in this case, number of processors that you spend to solve the problem. And then you see that, and then what you want to see is that the simulation gets proportionally faster as more computational resources that you put on and does not saturate. And what you see here is that the EPROC algorithm has some costs, but it scales nicely in the same way as the simulation with static synapses or STP would scale. Yeah, it's more costly than the more simple learning rules, but it scales in the same way. And the same you see here for weak scaling. Weak scaling means that you increase your problem size proportionally with the number of processors you invest. And what you would like to see is that the simulation time remains constant. And this is also what you see here, that this advanced learning algorithm still has this property. So you can now do these learning experiments with millions of neurons. And now you can ask yourself do these this relaxation of biological restraints, do they any good? These are very preliminary data, so you cannot trust them well. But these measure the energy consumption of a single compute node for static synapses, STP, the original EPROC, and our more biologically realistic EPROC. And you see that the energy consumption is of for the advanced learning algorithm is of course higher than for static synapses, but with the increased locality and less memory consumption, the energy consumption of our latest version is really a lot smaller. So apparently also the use of memory has an influence here, and this is what we are going to investigate next in the lab. For this, we first need to purchase more accurate energy meters and so on. So summary, the spatial temporal sparsity of brain offers opportunities for energy efficient AI. Our PD14 model became a de facto standard benchmark, but the impact on neuroscience remained limited. The model is still a challenge for neuromorphic systems, so not all of them passed them. For example, the Louis chip never made it. The community brought down simulation time and energy consumption by 2 orders of magnitude within just a few years. New models of larger scope and incorporating more precise data are coming up. Our multi-area model we envision as a useful first benchmark for the Spinnaker 2 system. And the ePros plus algorithm is a backpropagation like training with spikes compatible with biological constraints. It scales to millions of neurons. And we have first indications of superior energy efficiency compared to the time-driven approach, although we are still using a conventional computer here. Thank you.
Thank you, Professor Diesmann, for inspiring lecture. So, probably questions.
Yeah, if I remember correctly, the original eProp algorithm still had like was like basically organized in, maybe let's call it epochs now, for like you used to accumulate the error for some time and then you did like the backward.
Yeah.
So did I understand correctly that you removed this?
Yes.
Because this is how I understood like that spike update.
Oh, yeah. So this is let's see. So there are 2 steps. So updating the synapses only when the spike occurs is like a technicality. Yeah, that's important for event-driven simulation, but it does not change the algorithm. But what we did here in the eProp Plus is we apply the changes of the synapses continuously, not in a batch-like processing, yeah, where we all first accumulate the change and then do it all at once. Yeah, and yeah. Good.
First of all, thank you for this presentation. I want to mention, you mentioned something at page, I think, 24 or 25, when you mentioned the particle specific value. Yes. No, for the one page before. No, okay, I think you mentioned above that if we have an excitatory to excitatory, so it's equal to 1. And the excitatory to inhibitory is equal to -1. But also you mentioned that if it's 0.5, so it's going to be half by half separated. So what's the value of 0 will be, and also what's the value of -0.5 will be? Like if the
Yeah,
I want to understand if that's a mistake or it's like.
Yeah. So the expert is just sitting behind you, but luckily this is a relative measure of connection probabilities.
Yeah.
So the connection probabilities they can have any value. It's like the probability of making a synapse to an excitatory neuron minus the probability of making a synapse to an inhibitory neuron divided by the sum.
Okay.
And is this roughly correct?
This is correct, but the what you asked is also correct. So there's a mistake on the slide.
Oh.
And because you said if it's 50% E, 50% I, it should be 0. So yes.
Yeah.
Zero. Also, you can see this in this equation.
Sorry for that.
Yeah, the wrong thing.
But it's your slide, right? You made it.
Yeah. I like it. I think
Very good. Good point. Thank you very much.
Yes,
So how does EPROM, for example, affect the connectivity or connectivity in the network, right? The distribution of standard weights, for example. And the follow-up would then be, how does it affect the firing statistics in the networks? Because my feeling is that in the Markus Diesmann model, you get the correct statistics, activity statistics, because you have the correct connectivity statistics. But if the latter are changed by plasticity, then do you still observe the same, for example, frequency distribution, power, spectra, etc.?
Yeah. This is a very good point. In the original model, you're right. We created the connectivity, and the weights are just drawn from a Gaussian distribution. So when this distribution shifts or changes, the dynamical results can be different. Yeah, and basically we have no idea what it's doing. Yeah, and also one has to be really careful here, because if you would now start to change the weight distribution, you may discover that the network reacts very sensitive to this. Yeah? But it reacts very sensitive to all such changes because we purposefully removed all mechanisms of homeostasis on the network level, on the single neuron level. So it's not surprising that this model is brittle. So maybe if you do these things, you simultaneously have to add back some of the adaptive behaviors that we know from biology.
Yeah, it's less a critique of the model and more sort of a critique of plasticity almost, right?
Yeah.
If you have a plastic network that becomes more functional, so supposedly more like a brain, but it looks unexpectedly different from the brain. There's a tension here that I'm not sure of.
Yeah. So my idea of this in recent years is that maybe we are concentrating too much on the weights. So, for example, in the PE14 model, you can basically set all the weights to their mean value, and the results will be the same, because the irregularity comes mainly from the heterogeneity in the number of synapses per neuron. Yeah, but at the same time, the number of the neurons are so close that basically every pair of neurons touches each other, but only 10% of the potential synapses are realized. So one could also interpret learning as structural plasticity, so that synapses maybe are 0 and 1, but you move synapses. Yeah, and so we know that this is happening in biology, and maybe this is a mechanism that is as important as the weight plasticity itself.
And so I think, like, I mean, some of these statistics are right, not all. For example, like the distribution of firing rates would be actually if you look at the people data usually follow, you could say, of normal distribution, while it doesn't. Right? So, like, and I think there, if you want to fix this, what would be more plausible is to move away, like, from the standard additive gradient descent, right? Like where you say, okay, my new weight is my old weight plus something, plus my gradient. And there are also other ways of doing it, right? You can also have what's called an exponentiated gradient. You can multiply it by a certain factor, which will preserve the sign of the synapse, right? Firstly, right? You multiply by positive value. And also it will lead to log normal distributed weights, which then oftentimes translate into log normal distributed firing statistics. So like maybe this is also like a way of addressing this, like we're moving away from this additive. Because like probably also in biology it's not so additive always, like there are other things.
But would you expect the minimum to stay in the same place? So if you Okay, then you change from linear space to log space, and then you still stay additive, right? Linear to additive in log space rather than linear space. You multiplicatively. Yes, but then the minima, I don't see why the minima would change. So yes, you change, you stretch the landscape.
Yeah.
The minima of the energy stays. So then might be
this design. No, but I mean, like the minima can be realized by different, like 5 and 50.
the local minima should stay the same. If you fall into the same local minimum, regardless of how you get there, it's the same thing.
So they may be shallower, so it may be not shallow, yeah, less deep, so maybe switch.
I would say we fall in different minima.
Okay, you find it, okay, that's you find it. Okay, yeah, I find the difference.
Yeah,
You find the difference. You are satisfied, that's all.